Hello and welcome. Today, we're going to dive into some of the most essential language in all of math. We'll be breaking down domain, range, and this really powerful tool called interval notation. Basically, we're learning how to talk about the boundaries of functions with total precision. And trust me, this is a skill you absolutely have to have, especially as you get into stuff like calculus. So let me ask you a question to get us started. Imagine you need to describe all the numbers between, let's say, 2 and 10, but you want to include 2, but not include 10. How would you write that down in a quick, clean way that everyone understands? Well, that exact problem is what we're going to solve right now. All right, here's our game plan. First, we'll learn a new math shorthand. Then we'll talk about inputs and outputs. From there, we'll get into the rules of domain, figure out how to find the boundaries, and finally, we'll take a look at what this all actually looks like on a graph. Let's do it. Okay, first up, a new math shorthand. We're about to learn the language of interval notation. And seriously, think of this like a secret code that makes describing groups of numbers so much easier. You're going to see this everywhere. So what exactly is this stuff? Well, it's pretty simple. You use two numbers to show the start and the end of a range. But here's the magic trick, the part you have to remember. Parentheses versus brackets. Parentheses, the round ones, are like a force field. You can get infinitely close, but you never actually include the number. Brackets, the square ones, mean you're in. The number is included. That's the whole game, not included versus included. Now let's look at how this works in practice. This table is basically a direct translation guide from inequalities to our new shorthand. If x is just greater than a, no equal to, you use a parenthesis. But the second you see that little line underneath, greater than or equal to, bam, you switch to a bracket. And here's a pro tip. Infinity always gets a parenthesis. Why? Because you can't actually get there. It's an idea, not a destination. And this example just pulls it all together perfectly. We want all the numbers between -3 and 5, including them. The inequality has those or equal to signs, and that's our signal. On the number line, that means we use solid, filled-in dots. And in our final notation, solid dots means square brackets on both sides. So bracket, -3, 5, bracket. Done. All right, let's switch gears a bit. Now we're going to see how our new shorthand connects to the very heart of functions, inputs and outputs. This is where we get into domain and range. You know, I like to think of a function as a machine, like a smoothie maker. The domain is all the ingredients you're allowed to put in, and the range is all the possible smoothies that could come out. And this visual just nails it. The domain, that's your set of all possible inputs, your x values. You feed an x into the function machine, it does its thing, and out pops a y value, the output. The collection of every single possible y value you could get, that's the range. For the rest of this breakdown, though, we're going to zero in on the domain. What inputs are even allowed in the first place? So this is where the rubber meets the road. We're talking about the rules of domain. How do you just look at a function and figure out what numbers are allowed in? Well, funnily enough, the easiest way is to figure out what's not allowed. We're going to play detective and look for the illegal imports that would break the function. Let's start with the simplest case you'll ever see, a polynomial, like x squared minus 1. Now think about it. Are there any fractions here? Any denominators to worry about? Nope. Any square roots? No way. You can literally plug any real number you can think of into this function and it will work just fine. There are no restrictions. So the domain is everything, all real numbers. In our new notation, that's -infinity to +infinity, with parentheses. All right, rule number 1. This is a big one. The square root rule. You've got to remember that you cannot take the square root of a negative number. Not in the real number system anyway, it just doesn't work. So the rule is simple. Whatever is inside that square root sign has got to be 0 or something positive. It has to be non-negative. So let's put that rule into action. We've got the function with the square root of 5 plus 2x. What do? We grab the stuff inside the root, the 5 plus 2x, and we make a new little math problem. We say you have to be greater than or equal to 0. And from there, it's just basic algebra, right? Subtract 5, divide by 2, and we find that x must be greater than or equal to -2.5. In interval notation, that's bracket -2.5 to infinity. And now for the second golden rule of math. Seriously, you can never, ever forget this one. You cannot divide by 0. It's the one thing that just breaks math. It's undefined. So anytime you see a fraction, you have to make sure the entire bottom part, the denominator, never equals 0. So how do we use that? We take the denominator, here it's x squared minus 6x plus 8, and we hunt for the bad values, the ones that would make it 0.
We solve for when it does equal 0 by factoring it. We find that x cannot be 2 and x cannot be 4. Those are our forbidden numbers. So the domain is everything else. We write this in 3 chunks joined by that u for union. From -infinity to 2, from 2 to 4, and from 4 to infinity, all with parentheses to exclude the bad numbers.
Okay, you're ready for the next level? We've seen the square root rule, we've seen the denominator rule, but what happens when a function has both at the same time? Let's take a look. Aha, this is a fantastic example. We have a square root, but it's sitting in the denominator. So let's think this through. The root rule says the inside part has to be greater than or equal to 0. But wait, the denominator rule says the bottom can't be 0. So we have to obey both. The inside can't be negative, and it can't be 0. The only option left is for the inside part to be strictly greater than 0. We solve that, and we find x has to be greater than 2, which gives us the domain from 2 to infinity with a parenthesis.
I know that was a lot of rules to juggle, but it really boils down to a pretty simple process. This section gives us a handy checklist to make finding the domain nice and systematic. And this flowchart is your master key. When you get a function, you just follow the path. Does it have a denominator? If yes, set the bottom to not equal 0. Does it have a square root? If yes, set the inside to be greater than or equal to 0. Unless it's in the denominator, then it's strictly greater. And if it has neither, easiest path of all. No restrictions, the domain is all real numbers.
Okay, we've mastered the algebra. Now for the fun part, the payoff. Let's move away from the equations and see what domain and range actually look like on a graph. This is often where it all just clicks. Check out this parabola. For the domain, just ask yourself, how wide does it get? Those arrows show it's going left forever and right forever, so it covers the entire x-axis. Domain, all real numbers. Now for the range. Ask, how high and low does it get? Well, it has a clear lowest point, a minimum, at y equals -3. And from there, it goes up forever. So the range is from -3 to infinity. And since it actually hits that point, we use a square bracket.
Here's one more to lock it in. This curve has arrows pointing out left and right, and also down and up. It's just going to keep expanding forever, eventually covering every possible x value and every possible y value. So for this function, both the domain and the range are all real numbers, from -infinity to infinity.
And that brings us to our final thought. We've just learned a really powerful way to find a function's domain, just by looking for those algebraic restrictions. But what about the range? As we just saw, seeing it on a graph makes it super easy. But can you always find the range just by looking at the equation? The truth is, it's often much, much trickier. And a lot of times you really do need that graph to see what's going on. Just something to think about as you continue your journey in math.